pole OA weighing 2,400 pounds is hoisted into position by cables AB and AC. So here is the weight of our pole OA. It is known that the length of AB is 109.293 feet, and that the direction cosine in the x direction is this right here, negative 0.2562. Alright, so here's how I'm going to document that. I'm going to say RAB, the vector, position vector from A to B, the magnitude of it, the length of it, is 109.293. And I'm writing that because I know that we're going to have to make a position vector from A to B, and we're going to have to go through the steps in which we basically take this position vector and convert it to the force vector of that rope that's in the same direction of that position vector. So here I am here, just already getting in the mode of thinking, alright, position vector from A to B. And the magnitude, the length of this rope is this 109. You really want to get in the habit of sort of, documenting the problem information as you read through it. Alright, the direction cosine of this in the x direction is that. So, the cosine of alpha AB here will equal this number. Alright, moving on. In addition, the resultant of AB, AC, and the weight has components in the y and z directions only. Alright, the resultant of AB, AC, and the weight here. Alright, looks like, as far as I've read so far, there's only 3 forces here. Force AB, force AC, and the weight. And apparently, the resultant of these 3 forces has components in the y and z directions only. So 0 in the x, but we have some unknown component in the y and some unknown component in the z. Alright, the y component is known to be 2,000 pounds in the negative y direction. Okay, that's great. We actually know what this is. It's negative 2,000. Negative 2,000, because they say negative y direction. The z component is also in the negative direction, but with an unknown magnitude. Alright, so I'll give this a negative sign as well, to reflect that. Okay. Find AC and AB in Cartesian vector form, coordinates of B, tension in the cables AB and AC, magnitude of the resultant of these 3 forces in the z direction, and the angle in between these 2 cables, AB and AC. There it is right there, this thing. Alright, so let's start with part A. Let's put these 2 vectors, AC and AB, in Cartesian vector form. And when I read this, I'm really wondering, alright, does he mean the force vector or the position vector AC and AB? But, at the end of the day, we'll find both of them. So, I'll just start with the position vector now. So the way that I always think about this is final minus initial. The coordinates of B, your final, so the coordinates of B minus the coordinates of A, your initial. So the coordinates of A. That's how we make a position vector going from A to B. It's just final minus initial. So let us start with B right here. So looking at this point here, looks like B will have a negative x coordinate. So I'm going to write negative xb in the x direction. And it looks like we'll also have a negative y component. So plus negative yb j hat. And of course, looking at this picture, our point B here looks to be on the floor. Looks to be on the xy plane. So that'll be a z component of 0 k hat. Alright, now for A. Looking at point A here, it's going to have a x component of 0 it's out there on the y. It's going to have a y coordinate of 40. That is a 40 in the positive y direction. And we can see the z component right here as 69. Alright, so with these two pieces of information, I can do coordinates of b minus coordinates of a to figure out our position vector from a to b. So this minus this minus this, and so on and so forth. And if we do that math, we will get this position vector, and it's in terms of some unknowns at the moment, but we'll just have to roll with that. And I'll try to make position vector information blue, force vector information green, and couple moment or moment information yellow. Alright, so here's my three pieces of information about that position vector from A to B. And I want to see if I can squeeze as much information as I can from this. I don't like that we have these unknowns here. So we have the magnitude here. That's just the length of the cable, basically. We have our position vector. That's kind of unfinished. Not much we can do with that. But then we have this. We have these, remember the direction cosine angles. Remember what these direction cosine angles mean. These alpha, beta, and gamma allow us to completely specify the direction of any 3D vector, position vector, force vector, anything. So the cosine of alpha will equal the x component of whatever vector that is over the length of that vector. So if we apply that to our case here, the cosine of alpha of this position vector will equal the x component of this position vector, which we've narrowed down to be this, so negative xb, the length of this position vector, which we know, at 109, and actually, we already know what this is equal to. That's equal to this negative 0.2562. So we can do our math here and solve for what our x-coordinate is of b. So if I move my 109.293 and multiply it on the other side, what I'll get is, I get a positive 28. So that is the x-coordinate of b. So we'll write that in right here. Alright, so that was pretty helpful. We dove into our alpha. Let's see what we can come up with by looking at beta. Alright, so the cosine of beta equals the y component of our vector over the magnitude. And there's not much I can do here. I don't know what this number is equal to, like we did for alpha. And I don't know this, so that's two unknowns right there. Can't do anything here at the moment, but I'll save this for later. Alright, let's try writing out the gamma statement. Okay, so this isn't looking too bad. We can solve for our gamma right here by doing an inverse cosine. And if we do that, we'll get 129 degrees. Now, as soon as I find this, I think to myself, hang on, I have alpha and I have gamma. I'm sure I can use this equation right here to solve for beta. And with beta, that should unlock for me some information about the y-coordinate of b. Alright, so let's do that. We don't know what alpha is specifically, but we do know that the cosine of alpha is this number. So that negative 0.2562 squared plus the cosine of beta squared, that really is an unknown, plus the cosine of 129 degrees squared, all equal to 1 here. Alright, so we can crunch this math. We'll get down here, and of course we'll take the square root of both sides. Now remember, I'm going to get a plus and minus solution to that square root. So I'll do 2 inverse cosines here. And I'll get the first one as 42.8 degrees, the second one as 137.2. Alright, so take a look at our position vector again from A to B. Remember, every vector has a magnitude, a length, and a direction, usually given by some angles. And these angles are measured from a coordinate system based at the base of the vector, at the tail of it. So whenever you're discussing a vector's direction, you've really got to imagine an x, y, and z coordinate system based at its tail. So we have something to measure angles from. So in this case, the definition of beta is the angle from the positive y-axis to the vector itself. Now looking at that angle I've drawn, there's no way that's going to be an acute angle like 42 is. So it's definitely going to be the obtuse option, the 137. Alright, so here's our beta for our position vector AB. And now we'll bring it back to the cosine of beta so we can start targeting this unknown quantity here. So for my beta, I'll plug in that 137.2 degrees. And if we do our math, we can solve for our y-coordinate of B. 40.2. It's positive. Now, we got to be very, very careful here, and I just realized that I made a mistake before. This positive here, whenever you solve for an unknown in your system of equations, that positive means that your assumption was correct. My assumption here was that the y-coordinate of B was negative. So this number right here, just this number, not the negative here, just the YB symbol in that box will equal 40.2. So looking at this thing as a whole, the y-coordinate of B is negative 40.2. I actually made that mistake with the x here. I got a positive number when I solved for that xb, and I just, oh yeah, the x-coordinate of B is positive 28. No. We solved for xb and we got 28, but that means that this whole thing is negative 28. So the coordinates of B is going to be negative 28. And this guy right here should have a negative sign on it. My apologies. So one more time, we solved for YB and we got 40.2. That means just this tidbit right here. 40.2. Same thing over here. YB, boom, right there. 40.2. So all in all, the entire thing is a negative 40.2. And over here, negative 28. Lucky I caught that because I was looking at my picture. I'm like, wait. Definitely a negative x and definitely a negative y, like we discussed. So now with this number in there, we can complete our entire position vector from A to B. So negative 40.2 minus 40, negative 80.2. So let's change that. So here's my position vector, RAB. There we go. And also I picked up the coordinates of B as well. Here they are right here. B is negative 28x, negative 40.2y, and 0z. So now we'll work on the position vector AC. Alright, so hopefully position vector from A to C will be loads easier. Same process though. A position vector from A to C can be found by doing final C coordinates minus the initial, the A coordinates. So C is not too bad. Got a positive 32 in the X, a negative 36 in the Y, And of course it's on the floor, so 0 in the z. And of course we've already talked about a. Alright, so if we do coordinates of c minus the coordinates of a, we'll get, and now we have AC, at least the position vector AC, in Cartesian form. Alright, parts A and parts B are done, so now we'll move on to part C, the tension in cables A, B, and AC. We want to talk about the force vector now, so we're going to have to transform our two position vectors here into the force vectors of those cables. So we have the force vector for each one of these forces. What we're going to do is divide each force by the scalar of its own magnitude. So just make sure you really know what happens when you take a scalar and you multiply it or divide it into a vector. So by dividing each one of our position vectors by its own magnitude, we're going to shrink each one down to a length of 1, that is a unit vector. And then we can do scalar and a vector multiplication again. We can multiply each one of these unit vectors by the magnitude of the force that is in this direction, in that cable, and that will extend this unit vector into the force vector for that cable. So here's me dividing each component of our position vector by its own magnitude, including the magnitude itself by its own magnitude. So our new vector will be a vector in the direction of A, B. Its length will be 1, meaning it's a unit vector, but of course it'll still have components, x, y, and z, which will be these numbers. So I'll just crunch those. And now I'm going to multiply this vector by the magnitude of the force that is activated in this rope, which we do not know. So I'll just treat it as a symbol here, a variable, FAB. So this number will get multiplied into each one of these. And that will be our force vector AB. Alright, so here's our force vector for the cable AB. Alright, so I'll put that up here and I'll replace the position vector AB. We don't really need that anymore, I think. We'll see. Alright, and now we'll do this entire process for position vector AC now. Alright, so now we'll divide each component of AC by its own length, its own magnitude, to calculate our unit vector in the AC direction. So we'll get our unit vector components if we do that math. And of course now we want to multiply this entire unit vector by the strength, the magnitude of the force going in the AC direction. We don't know exactly what that is, so we'll just treat it as unknown. But this number is going to get foiled, in a sense, into each one of these quantities. And we'll get our force vector for the cable AC. And we'll put that right here. So now we want to add up all of our force vectors to get our resultant. We have force AB, force AB, force AC, force AC, and I can just write the weight vector real quick. And there's that. So now we just have to add up all the components of these three forces. We'll add up the x components and set that equal to the x component of the resultant, the y components, and set that equal to the y component of the resultant, and the same for the z. And from that, we'll get these three equations. So we have three unknowns, the force in AB, the force in AC, and the z component of the resultant, and we have three equations. So we have enough information to solve for our unknowns. That's great. So, I'll let you guys solve this however you want to. Me, I'll just put it in a matrix and I'll let the calculator do it. So if you solve that system of equations, you'll get these answers. And just remember again, this positive number here that we got for FRZ, that doesn't mean that the z component of the resultant is in the positive z direction. It just means that the assumption we made in the beginning was correct. And that assumption was that that z component was in the negative z direction, which wasn't really an assumption. We were told that, but I just like saying this. Also, you can just say that FRZ, just this little FRZ symbol right here, is that 4163.8 number. And altogether, it's negative 4163.8. Alright. So that is the tension in cables A, B, and AC, as well as part D, the magnitude of the resultant in the z direction. So lastly, we need to figure out the angle in between AB and AC. We can't forget about that guy right there. It's not too hard of a problem. We just have to use dot product. Before I forget, now that we know the magnitudes of those two forces in those cables, we can plug them right into here, in their unfinished force vectors in Cartesian forms. And we can actually write the complete force vector for these two forces. Alright, but moving on to this last part. So, AB, AC, I'll just pull up the position vectors for those. Alright, here they are. And I'll just put one of them in purple so we can have a contrast. So we can just use the dot product to figure out what our angle theta is. This guy right here. And we know all the information we need. We know the lengths of both vectors, the magnitudes, and we just have to multiply each component together and then add those up so we can get our cosine of theta by itself. So if we carry out this right here, we'll get 9960.2. If we multiply our two magnitudes together, we'll get 11749. And now we just have to do the inverse cosine of this quantity right here. And if we do that, we should get around 32 degrees. And looking at my angle here, that seems pretty reasonable. Alright, so long problem. Hope it all made sense. If it didn't, feel free to ask any questions you may have in the comments.